What if the order you teach mathematics in matters more than almost anything else you do? Not the standard that you're covering, not the curriculum you're using, and not the lesson plan you wrote on Sunday night. The order. The decision made, consciously or not, every single day about whether students understand something before they practice it. Because here is what I've seen in schools across the country, and stay with me here because it's going to feel a little familiar. Students who can execute a procedure perfectly, who can multiply two-digit numbers and follow an algorithm step by step and arrive at the correct answer every single time, and have absolutely no idea what they just did or why it worked. And so the moment the problem looks slightly different, the moment the context shifts even a little bit, the whole thing falls apart. Everyone is confused, right? Like the student, the teacher, the parent, because the student got it. Every practice problem, they got it all correct. So what happened? And here's the thing. Getting it and understanding it is not the same thing. And what that means is that we have been confusing them for a long time. Welcome to Show Me the Math Receipts. I'm Asali Smith, founder of Number Navigators, and this is episode 4. Today we're talking about one of the most consequential decisions in mathematics education. Concept before procedure. Understanding before fluency. The why before the how. The research has a clear answer, but it's not what most classrooms are doing. So let me set up the distinction quickly because this is where the whole conversation lives. Conceptual understanding means a student knows what's happening and why. They can explain it. They can connect it to something they already know. They can apply it somewhere they've never been before. Procedural fluency is that ability to execute a mathematical process accurately and efficiently. When fluency is built on understanding, it's one of the most valuable tools that we can give our students. But then when fluency arrives before the understanding is there, what we get is a version of fluency that's fragile. It works exactly as long as the problem stays familiar. The moment something changes, it breaks. And here's the part that makes this genuinely hard. That fragile fluency looks like success. It produces correct answers. It performs on certain assessments. And so we keep doing it, not out of negligence, but because the short-term feedback tells us it's working. It's only later in the next grade, in the next course, the next high-stakes moment that the bill comes due. The research on this has been building for decades. The National Research Council's Adding It Up, published in 2001, identified conceptual understanding as the foundation on which procedural fluency is built. These are not parallel tracks. One is the ground beneath the other. And then there's the work of Bethany Riddle Johnson and her colleagues at Vanderbilt, who've spent years studying how these two kinds of knowledge develop in relation to each other. What her research consistently showed is that conceptual knowledge is a more reliable predictor of procedural gains. When students come to a procedure already carrying some understanding of what it's doing, that procedure takes hold differently. It connects to something. And what that means is the fluency they build is not just faster to develop. It's more durable when the math gets harder. So let me show you what I mean. If we think about student A, they are asked, is 29 times 31 closer to 600, 900, or 1200? And the first thing they do is they reach for the algorithm. They set it up vertically. They start multiplying digits. They start regrouping. They regroup their work. They work their way through the whole procedure. And eventually they arrive at 899. So 900, they say, and they're right. But then there's another student, same problem. And instead of reaching for the paper, they pause for a second and say, well, 29 is almost 30, and 31 is almost 30. So this is basically 30 times 30? Oh, which is 900. Same answer. But what that student just showed us is that they already knew what neighborhood the answer lived in before they ever touched a procedure. And so the calculation, when they got there, was almost a confirmation of something they'd already sensed. And that is what I want us to stay with for a second, right? Because the algorithm is a reliable path to an answer. It is. But number sense is what gives a student a feel for the size of the problem before they start. And what that means is when they land somewhere, they have some way of knowing whether it feels right or whether something went sideways. You cannot build that kind of number sense by memorizing steps. It gets built through understanding what multiplication actually means, what it's doing underneath the procedure, and that gets built through concrete experience, arrays, equal groups, area models, and all of that. The experiences that give students a feel for the mathematics before we ask them to execute efficiently. The procedure, when it finally arrives, it's not a mystery to decode. It's a shortcut for something they already understand and have a foundation for. So if you are a classroom teacher, I want to name something that is true for a lot of people in your position. Teaching this way feels slower. It feels like you're behind when the class next door is already drilling the algorithm and your students are still working with arrays. I get it. And in a system that measures pace as a proxy for rigor, it feels real. And it costs something. But here's what I want you to hold on to. Every minute you invest in conceptual understanding before a procedure arrives is a minute you are not spending on remediation later. The student who understands what multiplication means before they ever see the algorithm is the student who can make sense of what happened to that understanding when the mathematics gets harder. The investment is made. The return compounds over time. If you are a math coach or an administrator walking into classrooms, the most interesting questions you can ask is not whether students are getting correct answers. It's what do students reach for when you ask them to explain themselves? Because those are not the same classroom. And over time, they don't produce the same outcomes. So here are your Wednesday morning receipts. 2 things for this week. The first, trace your sequence in one upcoming lesson. Ask yourself whether you're introducing a concept or a procedure. And if it's a procedure, ask what conceptual understanding you're assuming students already carry. If you cannot name that clearly, that is your gap, not theirs. And it's fixable. The second one takes about 30 seconds and you can start it tomorrow. After a student executes a procedure correctly, ask them, can you tell me why that worked? Not as a challenge, but as a genuine curiosity, as a signal that in this classroom, the answer is not the finish line. That question, asked consistently and with care, starts shifting the culture of the math classroom in ways that no curriculum can replicate on its own. And over time, students start asking it of themselves, which is the whole point. Fluency matters. A student who can move through mathematics confidently and efficiently, who has the algorithm in hand and knows how to use it, that's the goal. Nothing in this episode is an argument against efficiency or procedure as a destination. What that means is the sequence is the whole thing. The ground has to be there before the house goes up. Conceptual understanding is what determines whether a student can meet a harder moment when it arrives, and the research is clear on that. And so are the classrooms where I have watched it play out. You can have correct answers accumulating on the surface, a class average that looks just fine, and still have a soft ground underneath. At some point, the mathematics is going to shift. And when it does, understanding is what holds. So take the time. The fluency will follow. Next time on Show Me the Math Receipts, we are going into the classroom and talking about language, the words we choose, the questions we ask, the feedback we give every single day without realizing what it's communicating, and how all of it is either building mathematical identity or quietly dismantling it. You are not going to want to miss this one. I'm Asali Smith. This is Show Me the Math Receipts. And until next time, teach boldly, protect student thinking, and always keep your math receipts.